Okay, welcome to the set theory seminar. So today we have Matteo Viale again for the second part of his talk on absolute model companionship, forcibility, and the continuum problems.
Okay, thank you so much for the invitation. Let me make a brief recall of the main point I touched last time. So I introduced the strengthening of model companionship, which I call absolute model companionship. Then I introduced the notion of spectrum for this absolute model companionship. And then I outlined, well, that what we consider the right signature for set theory is the right signature of set theory. And that is the signature where you declare the delta zero formula to be equivalent to atomic formula. And then I started to formulate some results, but I just gave one. So let me just briefly recall the main definitions, and then in this seminar I will certainly state all the main results I have on this topic, and maybe I can also give the glimpse or at least some ideas on proofs of some of these results. Okay, so let's start with AMC. So definition, I just recall the definition. Definition: T is the AMC of S if T equals M such that M is S existentially closed, and T is axiomatized by pi2 sentences C such that C plus R for all is consistent for any R containing S. Sorry, for all val exist. So these are the Boolean combination of universal sentences. And if you have a pi2 sentence such that whenever you take a complete extension of S or some extension of S and the model of this extension, then you can find another model of your pi2 sentence and the universal and the universal fragment of the model. Okay, so this in case S is complete, then this amounts to say that for every model of S, you can find a model of well, actually, if in case S is complete, then this amounts to say that it's T is axiomatized by the pi2 sentence, which are consistent with the universal fragment of S. But if S is not complete, then you have to say a strong form of consistency. So it's not just consistent with the universal fragment of S, it's consistent with the universal fragment of any completion of S. Okay, so this is the way I like to formulate this notion of absolute model companionship, because it's saying that the notion of model companionship is characterized by maximizing the pi2 sentence, which is in the spirit of forcing axioms. What are forcing axioms doing? They are maximizing the pi2 sentence that holds true for HLF2. So the idea now is that I will get that HLF2 is the model companion of set theory. Okay. And now I move to the second notion, which is that of AMC spectrum. Well, maybe first let's use another characterization theorem. The following are equivalent. T is the AMC of S, and 2, T is model complete, and T for all val exist is equal to S for all val exist. So they share the same consequence when you restrict the attention to the Boolean combination of universal formulae. Okay, why I want to stretch this equivalence? Well, because this is easier to check. So when you want to show that a certain theory is the AMC of another theory, well, you just have to check this equality, which is maybe easy, it's a syntactic property, and then you have to check model completeness, which you can do again using a syntactic property. The most efficient way is to show that every universal formula is equivalent to an existential formula. Okay. So I move on. AMC spectrum. Well, I introduce the strategy to make partial scolemization of a theory, partial moralization of a theory. So I introduce two types of axioms for phi tau formula. Axiom 0 for phi is stating that for all x are phi x, if and only if phi x, where I added this relation symbol for each formula phi. Okay, so this is the way that usually one does the moralization of a theory. It adds this axiom for all the formulae of the language. And then I use this other strategy to add a Skolem function. So in this case, it's for all x. If my phi is giving a precise result to compute the witness, then I state that the witness is added by the relevant Skolem function, symbol of Skolem function that I added. Sorry, Px fx. So this is the first part, but if not, then I let my f phi. So I have this Skolem function on this tuple. I get value some fixed constant c tau. Okay. So in this way, there is no ambiguity. When I have a structure, a tau structure, well, maybe I have freedom to decide what is the value of c tau. But once I decide what is the value of phi tau, the interpretation of f phi is decided by the theory of M. Okay. And in the case that M has definable elements, so for example, the theory T has definable element, for example, in the case of the theory empty set is definable, I can decide that here I put always empty set, so there is no ambiguity. There is a unique extension of a ZFC model to a model of X1 phi. Okay, and now I play around. And I wonder, and I introduce the notion of AMC spectrum.
Everyone, welcome. I just want to talk about what's happening at New York Logic at their seminar this Friday. And also, Edward's bed and breakfast been going really well.
I don't understand really whether it's a question.
No, sorry, somebody was not muted and they were apparently listening to something else. I don't know, so I'm sorry about that.
No worry. AMC spectrum definition. A belongs to the AMC spectrum of a tau theory T if T plus X I phi phi I belongs to A has an absolute model companion, which I denote by AMC TA. Okay, and so this I was ambiguous. So A is a subset of the formula of tau times 2. So I decide whether I consider this formula as a tool to get a Skolem function or as a tool to get a relation symbol, depending on I. Okay. And then I start playing, and then I move to set theory. So, and the first point is write signature for set theory is some B contained can only be, well, it's better to say it like this, can only be the B containing delta 0 times 2, B contained in form epsilon times 2. Okay, so I declare that every delta 0 formula defines a good Skolem function and defines a good predicate. In this way, I have room, I mean, essentially all the absoluteness results that are established in Kuhnenstedt's book become expressible by atomic formulae. Okay, and even certain delta 1 concept become expressible by delta 1 formula, by atomic formula. Well, not atomic, Boolean combination of atomic formula, because the witness, if you compose to Skolem function, you are getting higher complexity. I mean, if you take the formula equivalent to the composition of two Skolem function, you may get outside sigma 0. You may get to delta 1.
Can I just ask, do you really need the names for the Skolem functions? I mean, if they are definable.
Well, I mean, the point is this makes many arguments smoother, but okay. I'm not sure that I really need. I could probably just go with the relation symbols, but then it would be a bit more annoying.
Yeah, so you would have to do, when you substitute these defined functions, you would have an
then
existential
I will have to
quantifier.
That certain notions are delta 1, because if you just substitute, they are sigma 1 or more, and you have to argue that they are simple. While in this way, it's more immediate. Okay. And then in this signature, I mean in the signature where delta 0 times 2 is considered as making, I mean, one makes add all relation symbol for the delta 0 times 2 set. Then you get that CH is sigma 2, Aleph 1 is defined by a sigma 2 sentence, or it's witnessed by a pi 1 formula, I mean, and so on and so forth. And now I start to list the result I can get. So theorem 1, assume B contains delta 0 times 2 and T plus, and T contains ZFC, and T plus T epsilon B has a model companion. Here I don't need the absolute model companion, I just need model companion. Then AMC TB, sorry, model companion of TB. Let me use this notation. Models ZFC epsilon B minus power set. So it models all axioms of ZFC. In particular, it models replacement. It does not model in principle the power set axiom. So it looks like, like the theory of H lambda for some regular lambda. Okay, so this is saying if I get an absolute model companion, what I get is the theory of some H lambda, or at least something that it is really close to the theory of some H lambda. But then I did the existence result. This is saying if there is something in this absolute model companionship spectrum, then it's going to be the theory of some H lambda or something very close to that. So, and now I have a series of existence results, theorem 2, for every, assume T contains ZFC, for every T definable cardinal kappa. What does it mean T definable? It means that there is a formula such that in theory T, this formula is a unique solution, and I'm adding the constant for the unique solution of this formula.
Could I just ask, Matteo, just a second, could I just ask, so why does the power set axiom not have to hold?
Well, for example, because you can get the, I mean, in principle, in some cases, it can be true that it satisfies the power set axiom. But in general, no, because it's a theory of H lambda. So for example, theory of H alpha 1 does not satisfy.
No, I understand that, but you're saying that this model companion, if it exists, doesn't always satisfy the power set axiom. So what's the problem with that? I mean, I understand, of course, that in H lambda it won't.
Well, if it satisfied the power set axiom, then it would be the theory of some inaccessible.
Okay.
Okay, and now you see now the theorem that I'm going to say. So look at what it says. Then there exists a kappa containing delta 0 times 2, such that a kappa belongs to the AMC spectrum of T, and AMC T A kappa is equal to the phi such that H kappa plus M models phi for M models of T. So you take all models of T, you compute H kappa plus in these models of T, and you take the phi that are true in these models of T. So it's really, it is saying that for every definable cardinal kappa, you can cook up a signature so that the theory of H kappa plus in this signature becomes the absolute model companion of set theory.
Can I ask, what does that mean in the first line? Assume T contains ZFC that for every T definable cardinal kappa. Like there's no kappa mentioned before there.
Well, I mean.
Oh, you're just fixing you're just considering.
Yeah, I'm assuming that
okay.
I mean T definable cardinal kappa means there is a formula which has a unique solution according to T, and this solution is a cardinal.
Right. Okay. No, I understand now. I just the way that it was formulated was confusing. Okay.
So
yeah, there should be a period after T includes CFC and a comma after every T definable cardinal kappa.
Yes.
Right. Yes. Well, okay.
Sorry, can I also ask a question?
Yes, T
so in this theorem 2,
yes.
Okay.
So in this theorem 2, there is, as we just said, this constant kappa, which does not come in the theorem 1. So how important is this constant for kappa? If I'm, for example, just interested in the theory ZFC with just signature without this constant kappa, do we still get an absolute model companion? Or?
Well, the point is, in general, if you take an arbitrary signature, most likely you don't get a model companion for that signature. So you have really to select certain subsets to find the model companion.
So this A kappa, is this going to basically introduce a constant for kappa, or somehow
it
a definition of kappa?
a constant for kappa, and then it introduces predicates for all the definable subset of the power set of kappa.
Okay. Mm-hmm.
So, for example, if kappa is omega, so you are adding predicates for the projective sets.
Okay.
And just one more thing, these models which feature in your theory, do they have to be well-founded, or doesn't matter
No, it doesn't matter. Whatever model. I mean, it has, since now you have the notion of what is kappa, it's the unique solution of a certain formula. You have a clear notion of what is H kappa plus according to the model. And then
does it matter if I restrict to just the well-founded models, do I get the same?
Two well-founded models?
Yes.
No, it changes. I mean, most likely you are changing the theory. You are not getting the model companion. It's too strict. I mean, it's too weak.
Okay, thank you.
Okay, can I move on? Is this statement clear?
Yeah.
Okay, so now we get to the theorem 3. There exists B star containing delta 0 times 2. Well, actually, I don't say more about this, but essentially B star contains a predicate symbol for the non-stationary ideal. So well, it will have a predicate symbol for the non-stationary ideal and a constant symbol for omega 1 and predicate symbol for a certain family of universally bare sets. And now you get such that ZFC for all T containing ZFC plus there exist class many. This is an overshoot. I mean, probably one can do with much less. For sure, one can do with one super compact and class many booting, just to make it simpler. Class many super compact. B star belongs to the AMC spectrum of T. T, and what are the T and and AMC of T B star is axiomatized by C. C is pi 2 in this signature, and for all M which model T and P in M such that M models P forces MM++, M force models that P forces C relativized to H omega 2. So essentially, this is saying the model companion theory for this B star is the theory of HLF2 in models of MM double plus. Okay. And there is more about this signature B star, theorem 4 for B star. If P for B star and T as in theorem 3, if P is a if T models T theorem 3 and V a model, so V epsilon a model of T, and C pi1 sentence of epsilon B star. So I consider the universal theory of T. Okay, then V epsilon models C if and only if V G epsilon models C for some or any forcing notion G V generic over P. So again, here I'm sloppy. I'm not assuming this model is transitive. I'm just assuming if I take a forcing notion in V, then V models the pi1 sentence if and only if the forcing notion forces the pi1 sentence. Okay. So what happens is that you cannot change the universal theory of V using forcing in this signature epsilon B star. You can just start to change the sigma 2 theory, but the universal theory you cannot.
Okay. So again, in the signature contained names for all universally bare sets, or what?
This is more delicate. I mean, it depends. I mean, you can play around. You have to put quite a bit of universally bare sets, but you can decide.
Okay. Okay.
Okay.
I
So
mean,
essentially, this signature is very canonical because now, what is the strategy to put a pi2 sentence in your model companion? Well, you force it because you start from an arbitrary model of T. You force over the arbitrary model that the pi2 sentence holds. Well, you didn't change the pi1 theory, so you satisfy the criterion to put a sentence in the pi2 in the model companion, in the absolute model companion.
Mm-hmm.
So this is tying this forcibility to let's say consistency or to being in the absolute model companion. In the previous case, for this theorem, this does not hold. In general, when you force over a model of T, you are destroying the pi1 theory of T. Because the signature is too rich. It has too many predicates whose properties are not preserved. But here the signature is quite rich because it has a predicate for the non-stationary ideal, it has predicates for universally bare sets, and so on and so forth, but you cannot change the universal fragment. So, for example, you can collapse omega 1. So, and you have a constant for omega 1. So it just says if you take a pi1 sentence regarding omega 1, you consider its truth value in V, where omega 1 is now becomes countable in VG, but the pi1 sentence remains the same if you reinterpret omega 1 correctly with the new omega 1 of VG. Okay. And now the why this is giving information on CH, theorem 5, for any B belonging to, and now it's important that I'm in the IMC spectrum, sorry, for any P containing delta 0 times 2, such that B belongs to AMC of T and T contains ZFC. CH is not in the AMC spectrum of TB. So CH is a sigma 2 sentence, so it's very likely that it is not, because the AMC spectrum is trying to make as many pi2 sentences as possible true. So you see, if you look at this notion of AMC spectrum, you're never going to have CH in some theory which maximize the pi2 consequences with respect to some signature. But on the other hand, the previous theorem tells that not CH is in the AMC spectrum, while not CH belongs to the AMC spectrum of TB star if T contains ZFC plus there exists class name. Okay, so this is giving really an asymmetry between CH and not CH. Not CH is falling in some model companion theory, in the absolute model companion of set theory enriched with some predicates. CH is never falling inside. Okay. But actually, we have more. We actually get the same for 2 to the LF0 less or equal RF2. So same hypothesis for any B containing delta 0 times 2. Yes, here I'm being let me go back to my paper because I don't want to say something too bold. Let me go to the statement. Okay, so yes, well, there is an hypothesis here. Sorry, if not CH plus T for all, well, actually well, let's say not CH plus T for all val exist is consistent. So actually, if T models CH and CH, so there should be two conditions which are very hard to satisfy at the same time. So you should have that T models CH and that your language is rich enough to transform CH in a pi1 in a Boolean combination of pi1 sentence. Okay, then you cannot put then CH can be in the absolute model companion. But even if T models CH, if your signature is not strong enough to make CH a Boolean combination of pi1 sentence, and in particular, it's likely that not CH is consistent with the fragment, with the universal fragment, then CH is not falling inside. And then I have a similar result for 2 to the LF0 bigger than LF2. And there is some C, well, some theta, pi2, such that ZFC plus theta deduce, well, actually, the optimal hypothesis is ZFC minus plus, ZFC minus power set plus there exists Aleph1 plus theta, deduce P omega is ordered in type omega 2, in type at most omega 2. And we also have that ZFC minus plus exists Aleph 2 plus theta deduce 2 to the Aleph 0 is less or equal than Aleph 2. And then again the same as before. If T for all well exists plus theta is consistent, 2 to the Aleph 0 bigger than Aleph 2 is not in the AMC of T. Well, sorry, if T plus TB. AMC. So what happens is if I choose my signature B so that this pi 2 sentence theta is consistent with the universal fragment of T as axiomatized in signature B, then I cannot put 2 to the Aleph 0 bigger than Aleph 2 in the AMC spectrum. And on the other end, theta belongs to the AMC of T B star. So you see, well, now if you look at this sentence, this is a pi 2 sentence. So before it was easy to put CH outside of the absolute model companionship because CH is sigma 2 and you want to maximize with respect to pi 2. So you should expect that you are putting the negation of CH in the AMC spectrum. But here you are taking pi 2 sentence and you are saying that provided your theory is not is not negating theta and it's not making theta too simple, then the absolute model companion cannot put continuum bigger than Aleph 2 inside. Okay. So I move on. And I get to the last theorem, Theorem 7, for B star as and T as before, and C pi 2. The following are equivalent. One, T for all val exist plus ZSC plus MM++ proves that C holds relativized to H omega 2. Some forcing T deduce that some forcing P forces C H omega 2. 3, same, but SSP, stationary set preserving P. 4, T deduce P max. Sorry, L, well, here it's delicate, L of UB, let's say. L of UB models P max forces C H omega 2. 5, C is honestly consistent. This is a notion of Ralph and David Aspero, Ralph Schindler and David Aspero. I don't say what it is. And 6C plus T for all well exist. Sorry, for all well exist is consistent for all R for R containing T plus T epsilon P star. So you see, and here, sorry, I have to be N slot T plus T epsilon P star. So you see, this is probability, this is forcibility in various degree of strength. So this is the weakest form of forcibility. This is a more difficult form of forcibility. This is another form of forcibility. This is actually weaker than forcibility. Okay, so the point is that honest consistency implies forcibility, but the converse is not clear. The main result of Aspero and Schindler is that forcibility overlaps with honest consistency. And this is consistency. I mean, not really consistency, because you still have to do this stuff of going to every model. But it's, I mean, it's the best form of consistency you can imagine. Okay, so you get probability overlaps with consistency, overlaps with forcibility to various degrees. Okay, and I think that that's essentially all the theorems I have about this AMC spectrum and what happens with set theory. Are there questions? I'm sorry, probably I rushed a bit and there are too many results. Some of them may not be entirely clear, so I can spend some time to go back on the statement of some theorem and try to clarify what I stated. No questions. Okay.
It's all completely clear. No, so I mean, I would kind of be interested in more details about what the signatures are, because that kind of affects
yes.
what pi 2
what
means.
is this B star?
Mm-hmm. Yeah.
So B star is it's a bit delicate. So no, sorry, I still have one theorem. Sorry, let me say the last theorem, theorem 8. Assume V epsilon models T as in theorem 3. So the following are equivalent for signature, well, that B epsilon models models MM plus, well, no, so models star for UB sets. So every dense set of Pmax, there is a generic filter, which means every dense set of Pmax coded by universal Hilbert set, and V epsilon models NS omega 1 is precipitous, and the theory of H omega 2 for in B star is the AMC of theory of V for epsilon B star. So you see that Boudin's axiom star, which is a very technical axiom, which I certainly won't have the time here to define, is equivalent to the statement that the theory of H omega 2 is the absolute model companion of the theory of V. Okay, so you give a model theoretic characterization of star. It can be expressed as a certain theory is model complete. So essentially, this amounts to say that the theory of H omega 2 is model complete. Okay, and now about the signature. Well, here I have been slightly sloppy because there is a delicate point I didn't say. B star can be many possibilities. Let's give one that gives a clear picture. B star equals delta 0 times 2 union well, so let's say epsilon B star is epsilon delta 0 times 2 union ns omega 1 and omega 1 union A is a UB set, sorry, A is a set of reals definable in L org omega, in the Chang model, without parameters. So you consider all the formulae which define some set of reals, relativized to the Chang model, and you add a predicate symbol for those formulae. And then this is the signature. You add the predicate symbol for the non-stationary ideal, a constant symbol for omega 1, all the symbols given by delta 0 formula and delta 0 Skolem function, and this type of universally Bird sets. So essentially, this is the minimal signature for which you can go, and the largest signature, B star, can also be epsilon delta 0 times 2 plus ns omega 1 plus all UB sets. Now you are working in a fixed model of set theory because, I mean, this is not a constructive notion. The point is that this is a constructive notion. This is a recursive signature. This one is not. I don't hear you, Gunther.
You push the paper up a little bit because
Yes.
the lower part is not visible.
Sorry.
Okay.
So in this case, you fix a model of set theory. You assume that you work in the real universe of set theory so that you have a clear notion of what is universally Bird.
And you're talking about
you add predicates for all universally Bird sets.
Okay. So for not just, I mean, so that's a proper class of sets that you're talking about.
No, universally Bird. They are in any case subset of power set of omega, so they are a subset of the power set of omega.
I see. All right. And so you add this constant for the non-stationary ideal. Does that?
No, it's not a constant. It's a predicate symbol. It's a unary predicate symbol.
I see. So you are able to check whether some subset of omega 1 is stationary.
Yes.
Yeah.
And here also these are added as predicate symbols.
Okay. And so does that is, so to speak, the stationary set preserving forcings, do they show up as a result of adding this predicate for ns omega 1?
Not really, because essentially the point is that Woodin has this result that using P max you can whatever pi2 sentence you can force In essentially, the result of Woodin says whatever pi2 sentence you can force in this signature, it holds in the H omega 2 of the Pmax extension.
Okay.
If you do this over the Chang model, for example, or whatever pi2 sentence you can force in this signature, it holds true in the H Aleph 2 of the Pmax extension of L of UB.
Mm-hmm. I guess I'm just wondering if you could do, similar things and vary the signature to capture different other things. Like, for example, I mean, this is totally naive, but there's this version of PFA where you preserve a Suslin tree, this PFA of S.
Okay, so
like
the point here that you are considering a theory T where you have a sigma 2 sentence that says that a certain tree is Suslin. So
Yeah.
you're adding a constant for the tree, or maybe,
Yes.
so you are making it essentially a pi1 sentence. So you add a constant for the tree and you say this is Suslin.
Right.
And now you look if there is a conditional version of star for this stuff. And
that was my question, yeah.
If you are, I mean, it's possible. I'm not sure that it can work, but it's something that one can try to look at.
Mm-hmm. Okay.
But I mean, the point is that you have to be able to prove Asper and Schindler's result for your class of forcing. So essentially, what you have to be able to do is to show that Asper and Schindler forcing they use to force a star is in your class.
Okay.
So if you can do that, then most likely you can do. But I'm not sure that it's an easy task because.
Okay. Very interesting.
Yeah, if you want, I can sketch proof of something, but I don't know if it's worth. I mean, some theorems are quite easy. They are not. The first theorems I listed, they are quite easy to prove. It's just a matter of the last theorems. They mix all things of Woodin, so they are more demanding. But let me just give an idea. So first observation is the following fact. Lemma H kappa plus epsilon delta 0 times 2 V A such that A is a subset of power set of kappa to the n is sigma 1 in V epsilon delta 0 times 2 V A such that A is contained in power set of kappa to the n. So what we see as Levi absoluteness is I erase this part. So here I'm adding many predicate symbols. Okay, and the standard proof of Levi absoluteness is this. You erase this piece and you say H kappa plus in this signature is sigma 1 elementary of with respect to V in this signature. Okay, but you can also add these predicates, and the proof is essentially the same of Levi absoluteness. The key point is that you are taking sets of bounded whose elements have a fixed rank, so that's why your proof works. If you allow unbounded subset, unbounded in rank, then you're in trouble. So, but then this is very good because it says whenever, I mean, this looks like a structure that realizes many pi2 sentences. For example, it satisfies the pi2 sentence, every set has size at most kappa, which is false here. So the idea is now I try to make this model complete. If I can make this model complete, then this result is telling me that the theory of H kappa plus is the absolute model companion of the theory of V. And the trick to make this model complete is you use the coding of, so you use that every A in H kappa plus is coded by kappa R for R a subset of kappa square. So what you do, you take the transitive closure of A and you take a binary relation whose transitive, okay? And if you check, this coding is very simple. Okay, so what you do is consider F contained in power set of kappa to the n, the union for n in omega. So I take I take a bunch of subset of power set of kappa to the n. Okay, and closed under projection, complementation, intersection. So essentially, I am closing off with respect to definability. So to existential quantification with respect to, okay. And now, now one can check that the theory of H kappa plus epsilon delta 0 times 2 F is model complete. Why? Because you can use well, I think let's see, maybe I can give an idea. It's really just computation of syntactic computation. You use the coding trick. So the point is that for X contained in H kappa, for X contained in H kappa plus, X is equal to code Y for Y contained in power set of kappa, and if X is definable, Y is definable. Okay, but now you have closed your family under projection, complementation, intersection. So essentially, you are declaring that the definable subset of the power set of kappa are defined by atomic formula, because for example, you have a set in the power set, a subset of a binary relation on power set of kappa. Well, the projection is in F, so it's now defined by an atomic predicate. Or the complement is in F, so it's defined also by an atomic predicate. So essentially what happens is that if your family is closed under projection, complementation, and intersection, you have quantifier elimination for power set of kappa, epsilon delta 0 times 2 F.
Could you push the paper up? Otherwise we can't see.
Yes.
Okay.
So if your family as this is closed under projection, complementation, and the like, and it contains, I mean, well, let's say the binary well-founded relation, then the power set of kappa with this stuff is as quantifier elimination. This structure as quantifier elimination. And now you use that essentially the map code maps quantifier free formula to universal formula. So what happens is that you start with a set X, which is defined by a very complicated formula. You take the pre-image. This is now a definable set in this structure. It becomes equivalent to a quantifier-free formula because actually it's a predicate of F.
So you take, sorry, for this Y to compute it from X, you will be redundant, right? So for every thing in X, you will have added many codes. Yes. Okay. Mm-hmm.
But nonetheless, essentially now suppose that X is defined by a very complicated formula. You pull back and now Y is defined by a very complicated formula here. But you have quantifier elimination. So the very complicated formula becomes an atomic formula. And now you pull forth and the atomic formula becomes a pi1 formula. So this is the general idea. Now, I'm sorry, I gave it very, very fast. And to prove, so using this idea, you get the first theorems. And let me just give a very rapid idea of how to prove the model completeness of HLF2 using Pmax. So the point is that this is the well known that M epsilon is well founded is pi1 foo. Sorry, M epsilon, so it's not so. M epsilon is iterable. So if one knows a bit of Pmax, M epsilon is iterable is a pi1-2 condition. And so the idea is now you say that H omega 2 models C for C some formula, if and only if for all M epsilon defined in a certain class, M epsilon models of C. Well, sorry, C of A, CA, and can be iterated to mapping small a to big A. So the idea is for all M epsilon, if there exists an iteration that maps A to A, then some A belonging to M to big A, then M epsilon models C of this small a. And if you think this is for all M epsilon, there exists an iteration mapping A to A, and M epsilon model C small a, this is pi2. Okay, so I'm really here, sorry, this is too fast. I cannot explain, but again, the idea is that you use, I mean, you use many tricks that Woodin employs all the time, but you have to make it in a, well, I need more time to detail on this. Sorry, this was too fast. Okay, so I think I stop here and hope that I didn't lose all of the audience.
Well, thanks a lot. I mean, I think it will take a little bit to digest everything, but I think at least some of us got an idea. So we had a few questions already. Are there any more questions from the audience?
Could I see Theorem 3, I think it was again?
I didn't hear what you asked.
Theorem 3, could we have another look at that? I think it was 3. Mm. Okay, maybe 4.
Oh, sure.
Sorry.
So theorem 3 is saying this absolute model companionship spectrum is axiomatized by the theory of HLF2 in models of MM++.
Yeah.
And theorem 4.
Okay.
So this theorem is saying you cannot use forcing to change the truth of pi1 sentences.
Yeah.
Sentences, watch out, this is important, it's sentences. So for example, A is uncountable for a certain set A. It may be true in V and it becomes false in the generic extension. But omega1 is the first, is the uncountable. This is true in V and it is true in the generic extension because you have a constant for omega1.
Okay. Thank you.
Okay, great. Any more questions? Okay. All right. Well, thanks a lot for this talk and for both talks, actually. And was there something? Somebody say anything?
No, I just said thank you for the talk.
Okay.
No.
All right, great. So yeah, we're gonna have another talk next week. So I'll see you all then.
And next
Okay.
week we're back to regular.
Yeah, regular time, exactly. Okay, all right.
Thank you so
Thanks,
much
Matteo.
for
Have a good
giving me
night.
the opportunity to talk here, and see you, well, maybe in presence at a certain point.
Oh, that would be nice.
Okay.